Hello, everyone. All right, so you hopefully have completed your table. We are trying to finish up and do a post-lab for our collision experiments. We did the collisions 2 days ago where we took videos of what was happening, and yesterday you guys were at the computers and you were analyzing those videos and you were trying to get the velocity of the two carts both before the collision happened and after the collision happened. So if you haven't already, I'm going to ask that you please get out the data table that you've been working on for the past 2 days. Okay? We're going to be analyzing it here together and trying to draw some conclusions from it. So as you guys are getting your data table out, we'll take a look at my data table that I have here on the screen. And my data table looks just like your data table, right? Like I've described the collision, we've got the values of the masses, we got the velocities before the collision, and we got the velocities after the collision, right? So let's start looking at this and seeing if we can get any kind of meaningful relationship out of all of these masses and all of these velocities, okay? So let's look at the first one. In my first collision, I had two equal mass cars where a moving car hit a stationary car. And if we look at my masses, they're not exactly the same, but they're awfully close, okay? So 1.38 kilograms and 1.31 kilograms. So the mass that I had in motion to start was mass 1. And it was moving with a velocity of 0.29 meters per second before the collision started. Mass 2 was the one that was stationary. After the collision was over, mass 1 is now stationary, and mass 2 is moving at negative 0.26 meters per second. Now, what do we notice about this? We notice that this negative 0.26 meters per second is very, very close to the negative 0.29 meters per second, isn't it? We'll have to see if that is an accident or if it's something a little more meaningful. Okay, in the meantime, let's maybe look at the second collision that I had. So my second collision was an explosion of equal mass cars. So an explosion means that at the beginning, both cars had a velocity of 0, and then at the end, one of my cars was moving in the negative direction, which is probably meaning to the left, at negative 0.22 meters per second. And then my other car was moving in the positive direction at 0.27 meters per second. Okay, so it's very interesting that before we saw that these velocities were very close in magnitude, and yet again we're seeing that these velocities are very close in magnitude. And in fact, if we look, the bigger mass seems to have a slightly smaller velocity than the slightly smaller mass with the slightly larger velocity. That's something that could be very interesting and we might want to think about a little bit more. Okay, so then if we have a heavy car and a light car, do we find the same stuff? So here's our heavy car, here's the light car. Our heavy car is moving, and then our heavy car is still moving at the end, and the light car is moving very quickly as well. And these don't show maybe as clear of a pattern, but maybe if we can come up with a pattern from analyzing maybe our first two collisions here, we can see if that pattern holds for these other three collisions. Hopefully they will. So we'll have to see. Okay, so let's think about this. We've got some masses and we've got some velocities. Now, if we look at the second collision, and we saw that the larger mass had a smaller velocity. Smaller mass had a larger velocity. Well, what if we multiply those masses and velocities by each other? So what if I take 1.38 and I multiply it by negative 0.22? Is that going to give me the same answer as 1.31 times 0.27? Because then that would kind of maybe even out the fact that one of my numbers is bigger in both cases and one of my numbers is smaller in both cases. And in fact, if I do that, so here we go, mass 1, velocity 1, for the second experiment, negative 0.3. And then if I do it for the second one, I get 0.35. Those are really, really close. So I'm on to something here. If I do it for experiment 1, do I find the same thing? Pretty much. Negative 0.4 is the value for my velocity, or for my mass 1, velocity 1 at the beginning, and mass 2, velocity 2 at the end is negative 0.34. So they're really, really close in magnitude. So this is looking good. And even if I kind of draw a line between my stuff that's happening before the collision, stuff that's happening after the collision, I can see that the stuff after the collision, if we add it up together, kind of seems like it might be equal to the stuff that's happening before the collision, right? And in fact, I did that over here. If I take the sum of this mass times velocity in the beginning, and then I compare it to the sum of the mass times the velocity at the end, I seem to almost show that these are exactly the same. Now I have to admit, okay, they are not exactly the same, right? So 0.06, 0.05, my worst one is 0.14, so they aren't exactly the same. But that's expected because, let's face it, we were working with these red carts that are, I don't know, maybe 50 years old. They've got a lot of internal friction going on. We certainly didn't have an ideal system to work with. And so to see that these things are not exactly the same is what we would really expect. But they're so close to one another, right? The change between what's happening before the collision and what's happening after the collision is really, really pretty small. So that must mean that we've got some kind of a pattern here. And that's a pattern that is going to be the focus of our unit here, this unit 9. Okay? That pattern, we have a name for it. We're going to call it momentum. All right, so we've been waiting for a long time to be able to use this word here in class, and it's finally arrived. We're finally going to start talking about momentum. So, what is it? Momentum is mass in motion. Okay, so if we wanted to put a definition to it, that's really what we got. Momentum is mass in motion. That's what it's describing. And if we think about the unit for that, it is mass, it is in motion. The unit for mass is kilogram. The unit for our velocity, which is what we're describing when we talk about motion, is meters per second. So the unit for momentum is going to be kilogram meters per second. It is just that simple. We're sticking them together. Okay? Okay, and some things to know about momentum. Velocity is a vector quantity, okay? We know that direction matters for velocity, and we saw it in my table right here. The fact that sometimes I had negative velocities, and that was very, very important. Those negative velocities mattered. They were different than positive velocities, and that meant that my momentum, my mass velocity, my mass in motion was also going to be either positive or negative, and that matters. I do want to keep that, okay? The direction of the momentum vector is the same as the direction of the corresponding velocity vector. Okay, so velocity is a vector, which means momentum is a vector. And since this direction matters, positives and negatives are going to matter. You're going to have to keep good track of them during this unit. Okay? So if we are going to have an equation that is going to describe this momentum, the equation is going to be momentum, which here is denoted as P. It used to be called progress before they decided to call it momentum. So this would be like back in Newton's day. They called this value progress, which is why it's denoted by a lowercase p. But now we call it momentum. And so momentum is equal to your mass, again measured in kilograms, times the velocity. So not too bad. It's not too bad of an equation. As long as you can remember that lowercase p means momentum, m and v is stuff that we've already worked with, and so this one is a short and sweet, easy equation to remember. P equals mv. It is momentum. And so what I would like for you to do is I would like for you to turn to your data table. And what I would like for you to do for tomorrow is I would like for you to calculate You only have to do this for one collision. So I did it for all 5, but I'm going to ask you guys to only do this for one collision. I would like for you to calculate the momentum that you have at the beginning. So I would like for you to calculate mass 1 times velocity 1 at the beginning. I would like for you to do the same thing for mass 2, so m2, velocity 2 at the beginning. And then I want you to calculate the momentum at the end. And then afterwards, I want you to compare them, okay? So I want you to see, ooh, I don't want to do that. Get out of there. I would like for you to determine for yourself, did you end up seeing any kind of like a conservation of momentum here? So calculate all of your momentums, all of them right here, and then I want you to sum those momentums that you had at the beginning. I want you to sum your momentums at the end, and I would like for you to show me if you had any kind of conservation of momentum in your system. We're hoping to see that since we have no outside forces acting on our system, that we would see a conservation of momentum. So I'm going to ask you guys to do that. It is going to be a part of the lab summary that you will turn in to me on Friday. Okay, so you have that little half sheet that I passed out to you today, or yesterday, and you'll see that on that half sheet, doing this small calculation is going to be a part of your grade. Again, you only have to do it for one collision, all right? All right, so let's talk about that conservation of momentum. Okay, we've talked about other conservation principles before, so this one is not going to be wildly different. Okay, conservation of momentum just means that the amount of momentum present before the collision is going to be equal to the amount of momentum present after the collision. So what they're really trying to say to you is that momentum at the beginning is going to equal momentum at the end. And something that I want to add to that is really just that this is always going to be true as long as there are no outside forces acting on our system. That is it. We should always see conservation of momentum if that is the case. All right? So we, of course, have more than one way to talk about momentum, and we have 2 different categories for momentum. Now, your lab, you investigated one of these categories for momentum. What you guys did is you investigated what's called an elastic collision. Now, we were using the carts, the red carts, and we were always using the plunger end of one of the carts, which means that these carts were always bouncing off of one another. And anytime we've got something that is going to hit and bounce, we have the possibility of having an elastic collision. And usually that hit and bounce is kind of like a key word that tells us that we're looking at an elastic collision. Okay? So what happens in an elastic collision? Well, momentum is conserved, okay? As long as we have no outside forces, no outside net force acting on our system, we're going to have momentum conserved. But the thing about an elastic collision is that kinetic energy will also be conserved. If you guys remember from last unit, kinetic energy is equal to 1/2 mv squared. Since momentum also deals with mass times the velocity, these 2 things are really dealing with kind of the same quantities. So in an elastic collision, both of them are going to be conserved. The amount of kinetic energy I have at the beginning is going to be the same as the amount of kinetic energy I have at the end. The amount of momentum I have at the beginning is going to equal the amount of momentum I have at the end. Okay? And since these things are bouncing apart, they both have the possibility of changing velocities. So what I have written on here is not a new expression for momentum, but it's a kind of a way to express conservation of momentum in an elastic collision. Okay? So what I'm really saying with this, and I would highly recommend putting this into your notebook, is we're saying that the momentum of car 1 at the beginning plus the momentum of car 2 at the beginning is equal to the momentum of car 3 at the end, or car 1 at the end, plus the momentum of car 2 at the end. That's really all this equation is saying. And because these things are, kind of hitting and bouncing, the velocities of each could be different. All of those velocities have the potential to be different, okay? The other one that we could have done with those red carts, but we didn't end up doing, would be an inelastic collision. So I have a video of an inelastic collision that I would like to show you. Okay? So, can we make this bigger? Let's see. Okay, sorry, that took me a second too, but here we go. So here we have an example of an inelastic collision. So it's the same two carts that you guys were using before, but now I'm using the Velcro on the ends instead of the plunger. And what we see is that one cart is stationary, one cart is moving, and they come together, and in this collision, they actually stick to one another. So there is no bouncing here. And cart 1, here we go, it's moved very quickly, and then when it sticks, we can see that these two are moving much, much more slowly than car 1 was by itself before the collision. Okay, so this would be an example of an inelastic collision. And the hit and stick kind of mantra is going to be a really good way to remind yourself, or kind of a signal to yourself that, yeah, this is going to be an inelastic collision. So, even though this is an inelastic collision, momentum is still conserved, okay? Again, momentum is always going to be conserved unless we have an outside force acting upon our system in a collision. But the difference here is that kinetic energy is not going to be conserved. So in this one, we're talking about, a lot of kinetic energy can be kind of transformed into dissipated energy due to crumpling, due to sound, due to a lot more heat. That's usually kind of like the telltale signs that your kinetic energy is not going to be the same, and so that's going to be an inelastic collision. And so what I have for you here is I have another equation. Again, this is not a different equation, really. It's really just another equation that describes to you conservation of momentum, but now we're talking about it specifically for an inelastic collision. Okay, so the mass times the velocity of mass 1 at the beginning plus mass 2 times velocity 2 at the beginning is equal to mass 1 plus mass 2. They have stuck together. And since they have stuck together, they must have the same final velocity. So we can do mass 1 plus mass 2 times that final velocity. Okay? So, what are the new things that you have in your notes? Well, you've got these new definitions, but we also have quite a few new equations, right? P equals mv, and then specifically those conservation of momentum equations. So let's get some practice using them, okay? So we got some practice problems. We have got a 36.4 kilogram Pee-wee football player. He runs and he plows into an 80 kilogram referee, and the referee flies forward at 5 meters per second. Let's assume that this is a perfectly elastic collision, and we want to know what would the final velocity of the football player be. So, perfectly elastic collision. So we're going to be using this guy, okay? There's no outside forces on this collision. It's just the kid and the referee. There's nothing else pushing them or anything. So we know momentum will be conserved. And we're going to use this elastic collision equation to help us solve this, okay? So let's write out what our knowns are. And I'm going to make this pen a little bit skinnier so that I don't waste a ton of space. But we got mass of the kid. We're going to call him M1. So that is 36.4 kilograms. We've got the mass of the referee. That's going to be mass 2. That is 80 kilograms. Okay? That little kid, he is starting to run at 8 meters per second. And then we know that in the end, let's see, do we have enough information? solve this? We do. Okay, we know that the velocity of the referee in the beginning is 0 meters per second. He's just standing there. So then our velocity of the little kid at the end, we want to know what that is, but we do know that the velocity of the referee at the end is going to be 5 meters per second. So this is everything that we know. So let's see, we are going to use m1 v1 plus m2 v2 at the start is equal to m1 v1 plus m2 v2 at the end. Let's fill in what we know. Okay, so 36.4 kilograms times 8 meters per second plus, well, I already know that the velocity of our referee at the beginning is 0, so I know that this whole thing is going to end up being 0. I'm just not going to bother with it. So really, I know that this is going to be equal to the mass of the kid, 36.4. Oops. Not 3.64. We want 36.4. Times his final velocity plus the mass of the referee times his velocity. Okay? So what are we going to do? Well, we've got that 36.4 times 8 is 291.2 kilogram meters per second. And let's subtract this quantity over here so that I get my unknown all kind of by itself. So we'll say minus, and this is 80 times 5. That is 400 kilogram meters per second. Has to be equal to 36.4 times that velocity that I'm looking for. So 291.2 minus 400 is going to equal negative 100, oh man, 108.8 kilogram meters per second is equal to this 36.4 VF. So let's divide everything by 36.4 kilograms. And we should get that his velocity is negative 2.99 meters per second is the velocity of our little pee-wee football player. Okay, so he is actually thrown backwards by running into this ref. But think about it. He is way smaller than this ref. You guys did a couple collisions where you had a light cart hitting a stationary heavy cart, and you saw that that light cart went backwards. So this answer seems to make sense with what we know from the lab. So I say that this is good. We are good to go with that. Let's do another example, though, because this is just an example of inelastic collision. So let's look at an example for an inelastic collision. Okay, so we have a ball that has a mass of 3 kilograms. So here's our 3 kilogram ball, and it is moving eastward at 2 meters per second. Okay, and it strikes a mass, or a ball that has a mass of 1 kilogram, and it is moving at 2 meters per second westward. The balls stick together after impact, and we want to know what is the magnitude of direction of the velocity of the combined mass after the collision. So what do we notice right away? We notice the stick together. These things stick together, so we know that this time we're going to be dealing with an inelastic collision. So since we, again, have conservation of momentum, there's nothing that is acting on our system. Okay, nothing else is touching this ball that's moving west and the ball that's moving east. So we've got conservation of momentum. We're going to use this equation to help us. All right? So let's do that. So we got m1 v1 plus m2 v2 at the start is equal to m1 plus m2 times their final velocity. So let's fill all this stuff in. Okay, so I'm going to say that positive is moving to the right, because that's usually what happens in standard coordinates anyway, but we need to define it. So we'll say positive is to the right. So we've got a 3 kilogram mass, and since it is moving, in fact, to the right, we say that this is going to be a positive 2 meters per second, plus a 1 kilogram mass that is moving at a negative 2 meters per second. And this is equal to 3 kilograms plus 1 kilogram times their final velocity. Okay, 3 times 2 is 6. 1 times negative 2 is negative 2. So 6 plus negative 2, this is 4 kilogram meters per second, is equal to 3 plus 1, well, that is also 4 times VF. So let's divide everything by 4, and we get that the final velocity of these two balls that have stuck together should be 1 meter per second. All right, we're good to go. So you guys are going to have a worksheet that is going to ask you to try out some of these problems with elastic and inelastic collisions, okay? So we're talking about conservation of momentum the whole time. Please refer back to this video if you need to. I will post it onto Edmodo so you can access it anytime that you like. And otherwise, I will see you guys tomorrow, all right? Have a wonderful day.